Rotational kinetic energy. In a closed system where the net external force equals 0, the total mechanical energy is conserved. And if we applied a net external force for some distance, it would do work, and we could change the total energy of the system. So, in a closed system where net torque equals 0, continuing our analogies, our total mechanical energy is still going to be conserved, but now we're going to include rotational kinetic energy. And again, continuing our analogy, if we apply a net external torque for a distance, or, well, an angle, we can do work and change the rotational kinetic energy and therefore the total mechanical energy of the system. So looking at our equations, in translation, we have kinetic energy in joules, 1/2 mv squared, and work also in joules, where it was your net force times the distance. Remember, here it's the dot product, so it was only in the same direction as that distance. Okay. In rotation, it's rotational kinetic energy, also still in joules. Energy is energy is energy. It doesn't matter what form it's in, we still measure it in joules. Okay. But here it's K equals 1/2 I omega squared. Remember, I is our rotational equivalent of mass, and omega is our rotational equivalent of velocity. And again, work is still in joules, and it's now our net torque times our distance, or our change in angle. And we can also write that, remember, net torque is going to equal I alpha, and then your distance is really actually the angle that you've gone around. And a quick note about rolling objects. If I have something rolling up or down a slope without slipping, that's our way of saying that there's no translational kinetic energy to worry about. We're converting potential energy either to or from purely rotational kinetic energy.